All right, so 5.1 of velocity head, right? Yeah, so that's referring back to this conservation of energy equation. The simpler version is where we're at right now. That's this critter. So H1 is going to be potential energy head. The second statement, velocity squared over 2g, velocity head. P2, that's not P squared, that's P2, over the specific weight. That will be your pressure head, and then this is also another velocity head. So velocity head is V squared over 2g. Given a velocity of 6.21, pretty simple. What'd you end up with for the velocity head? 26.6 feet. So yeah, just make sure your units work out to feet on all the heads. So any heads that you're working with. All right, second one, they want a pressure head. So that, what's that equation?
Over the specific weight of water.
Yep, P over the specific weight of whatever fluid. So if it's water, it's water. Yep, it's gonna be water most of the time. So then you just take the pressure. What's the specific weight of water? Yeah, so what'd you get for? So this is just going to be collecting the different energy forms of a hydraulic system. Seven wanted velocity head again? Yeah. Oh yeah, I went back to the earlier problem, which had the 4.25. Yep. What'd you get? 0.28 feet. All right, pretty simple. Let's get rid of those. Yeah, yeah. Have that one for sure. So keep in mind that that equation, this conservation of energy equation, is going to be only applied to this kind of system where we have a open reservoir. So it kind of,
whole equation, yeah.
huh?
That whole equation right there.
Yeah, it's that is the simpler form. So we're going to add friction to it and also entrance loss. But yeah, this equation. So when you see this, this applies to this kind of system. So when we have closed systems, this is an open system. When we have closed systems, it will be a little different. There is the, there we go. All right, so the more complicated version, getting a little more complicated, adds friction losses. So that is an H sub L, it should be. So it says this H sub L is going to represent head loss due to friction and other factors. So other factors can be like entrance losses. So some entrances, the pipes are different. You know, some will have a gate valve that can be shut off. There could be a loss due to that gate valve, even though you have a 2-inch gate valve and a 2-inch pipe, right? Let's say we have a 2-inch diameter pipe and it comes into a gate valve and then it goes through that into some kind of an exit. There's restrictions inside those gate valves. They're not the same diameter as the 2-inch pipe. So there can be losses for any kind of fittings or valves. And then there can be entrance losses, like how the water gets into the system. losses. So we don't calculate entrance losses. Typically, they're given to us. So based on whatever fitting is there going into the pipe, they'll give you an entrance loss for it. So that's something that we won't calculate. And that would be H. So E. So E would be an entrance loss. That would also get plopped in the equation. So the friction factor we can calculate. That's this equation. So one of the H sub L losses is H sub F friction. So really there's only two. There's friction and there's entrance. But this is a kind of a complicated little equation. Has lots of variables, it defines them there for you. But if you're looking for the friction head loss, that's H, that's what the equation is. Right? If we're looking for how much energy we lost due to friction, we want to solve this equation, but we need to know several things. We need to know F, the friction factor, and then the rest of this we usually have, like we better have the length of pipe, we better have the diameter of the pipe, we better have the average velocity, right? And then we also know what G is. So the bottom variables, typically you have L, D, V, G, right? Kind of the whole fractional part of the equation. You just plug in what you have. The thing that we don't typically know is F, the friction factor. So that one we